Hi, I'm Jono Lee. Today, I'm excited to present our work, Is There a Better Source Distribution Than Gaussian?, published in TMLR 2025. This is a joint work with my co-first author, Kwan-Seok Kim, and our corresponding author, Professor Jun-Seok Lee. The motivation of our work is simple. Unlike diffusion models, flow matching offers the advantage of allowing a free choice of the source distribution. However, almost every model still differs to the standard Gaussian. This raises a key question. Can we design a better source distribution that leverages the actual structure of the data instead of using a generic Gaussian? To answer this question, we first needed a way to visualize the learning dynamics effectively. So, before designing a better source distribution, we proposed a novel 2D simulation framework. Distributions in high dimension behave quite differently from the low dimensional ones, which we are intuitively familiar with. In low dimensions, a standard Gaussian concentrates its mass at the center or origin. However, in high dimensions, the mass actually concentrates on a thin spherical shell, effectively resemble a hypersphere. However, existing naive 2D simulation failed to capture these high-dimensional geometric properties. Therefore, to address this limitation, we proposed a novel 2D simulation framework designed to reflect these high-dimensional properties. Next, based on this framework, we formulated several hypotheses regarding the source distribution and verified them using our 2D simulation. The first hypothesis is density approximation, which means the closer the source distribution approximates the target density, the better the performance. Surprisingly, the answer was no. As we approximated the target density more closely, from weak to strong, the performance actually degraded. But why? We attribute this degradation to mode discrepancy. The approximated source tends to miss the low density modes like this. Then what about aligning just directions with target? If we align the target too tightly with the data directions, generation quality degrades. However, when the source provides sufficient angular support, generation quality improves. We attribute the degradation in tight alignment to path entanglement. When the trajectories are overly constrained to a narrow area, too many distinct target paths must be learned in a confined region. This creates complexity intersecting dynamics, making the vector field extremely hard to learn accurately. The next part is understanding the learning dynamics of flow matching. In this part, we analyze the behaviors of representative training methods, specifically independent I-CFM and optimal transfer CFM. As you know, I-CFM employs independent coupling. Since the Gaussian source is directionally uniform, each data point matched with source samples from all directions uniformly. We can clearly verify this in the trajectory density heat map in the middle. This creates what we call an omnidirectional learning effect. Because it learns flows from every direction around the data modes, it yields a robust vector field that covers a wide space, although the convergence is relatively slow. In the case of OT-CFM, the model performs optimal transport pairing within each mini-batch. Consequently, the matching probability decays within distance. This means that instead of learning from all directions uniformly, source samples are primarily paired with nearby target points, leading to highly localized trajectories. This consistent pairing creates straighter paths and leads to faster convergence. However, this leaves the vector fields in inner regions undertrained, making the model fragile to outliers. To summarize our findings, I-CFM benefits from omnidirectional trainings, yielding the robust vector field, but it is less efficient. In contrast, OT-CFM is highly efficient because it learns specific paths more frequently, but this focus makes it fragile to outliers. Having analyzed the distinct characteristics of each method, we now address the common problems shared by both approaches. There are two major issues. First, both methods consistently fail to generate samples when initialized from low-density directions. Second, there is a substantial norm gap between the source and target distributions, which imposes an unnecessary burden on the learning process. So, to address these issues, we propose sampling strategy for failing in low-density directions, and we propose norm alignment strategy for large norm gap. So, let me introduce these proposed methods. The idea of pruned sampling is quite simple. Train on the full Gaussian to ensure robust coverage, but during inference, we simply prune the starting points that corresponding to these low-density data-sparse directions. This is applicable to any pre-trained Gaussian FM models. For large norm gap, we simply align the expected norm of the target to match the source. This bridges the scale gap and simplifies the transport task. So let's move on to the result part. Here is the table summarizing the results for the baseline, pruned sampling, norm alignment, and the hybrid approach. First, let's look at pruned sampling. It consistently improves performance across all NFV compared to the Gaussian baseline. This confirms that removing data-sparse directions is always beneficial. Second, norm alignment shows a distinct trade-off. While it significantly boosts generation quality at high NFS, it actually degrades performance at very low NFS. Finally, applying both methods together, the hybrid version achieves the best results in high NFV, but degrades performance at very low NFVs, just like norm alignment. So, we want to know why norm alignment causes degradation, specifically in low NFVs. Using our 2D simulation, we discovered that norm alignment significantly increases the curvature of the trajectory compared to the baseline. As you know, when curvature increases, the OD solver requires more steps to approximate the path accurately. This explains the reason why norm alignment degrades performance when the NFA is low. So, in summary, we started with a fundamental question. Is there a better source distribution than Gaussian? To answer this, our contributions can be summarized like this. First, we proposed a novel 2D simulation framework that accurately preserves high-dimensional geometric properties. Second, through this simulation, we derive critical findings that provide practical guidelines for designing effective source distributions. Third, based on these insights, we propose novel source strategies, pruned sampling, and norm alignment. Finally, We demonstrated that these simple yet effective methods lead to significant improvements in generation quality. We hope our work provides a solid foundation for future research in source distribution design. Thank you for your attention.